Okay, so now we're getting to something called system. So basically, how do when there's multiple objects, how they interact together. Again, it's starting to get into more realistic things because we know there's not like isolated objects in space. It's just usually there's, like, if you think about the human body, for example, it's your arm. Here's your forearm, your hand, your wrist, your fingers. They're individual things that are connected together to make a whole. So for this example, we're gonna, like in physics 11 and 12, we look at like almost like 3 objects connected together. But here we go. We're looking at 2 objects right here. We have a 20 kilogram object connected to a 10 kilogram object by a rope, and we're pulling on the right side with a force of 150 newtons. So our first question is, what is the acceleration of this system? So when doing these ones, it's often easier to think of it as a whole first. So I'm going to look at this object as a whole. And we're looking at it with no friction to start with. We'll look at this friction scenario later on. So basically what I mean by is look at the system as a whole. We're first going to think of this, instead of thinking of it as 2 separate objects, we're going to think of it as a single 30.0 kilogram object. Okay? And this 30.0 kilogram object is being pulled with a force of 150 newtons. So from here, it's pretty straightforward. We say, okay, F net is equal to MA, and that's equal to the sum of the forces. And of course, there's the normal force and force of gravity as well, but I already know there's going to be equal and opposite from each other, so I'm not going to bother drawing it. There's no friction, so I don't really need them anyways. So we know our mass is 30.0 kilograms. Our acceleration, that's what we're trying to find. And the thing that's pulling is just that 150 newtons. Again, if there was friction force, we'd then subtract the friction force. Divide both sides by 30, we get 5.00 meters per second squared. So it's saying that by pulling the system with 150 newtons of force, it's all going to accelerate at 5 meters per second squared. This is the more challenging and more interesting part, though, is what is the tension in each string? Now this first string, it is what it is. This one is 150 newtons. Pull with 150 newtons. The action-reaction force is 150 newtons. This is it's experiencing a force of 150 newtons. The question is, what is happening in between? So what we need to do is Newton's third law states that for every action there's equal and opposite reaction. So basically this 10 kilogram block is pulling on the 20 kilogram block, but at the same time the 20 kilogram block is pulling on the 10 kilogram block. So basically what's happening, this 10 kilogram is pulling on the 20 kilogram block. At the same time the 20 kilogram block is pulling on the 10 kilogram block. So we draw the forces like this, T and T. So if I actually were to draw the overall F net equation for this expression, we get F net is equal to MA, which is equal to, there's that 150.0 newtons. But what is also there, which I didn't draw, is we can see that if to the right is positive, it's plus 150, but then we can see there's that minus T. Like this is our first order, subtracting that T. That T is in the opposite direction of 150. But then we're adding the second T. So what actually ends up happening is the T's cancel out. That's why we can think of it as a single 30 kilogram block. However, by looking at it as a whole, it doesn't tell us about what's happening in between. So now if we want to solve for B, we have to look at one or the other block separately. So it doesn't matter which one we look at, but we have to just look at it separately. So for example, if I call this block 1, this is block 2, and this is block 1. Okay, so if I look at block 1, if I draw just the free body diagram for block 1, we know it's being pulled to the right with 150.0 newtons. It's also being pulled backwards with some tension T. So if I now write out my net force equation, I have MA is equal to that 150 newtons minus T. So this is block 1, so I'm going to go M1. M1. So we can see, okay, I rearrange for T. T is equal to 150.0 newtons minus M1A. So we just found A. So that's why we have to solve for the system first. So 150 minus the block is 10 kilograms acceleration is 5. So we get 100 newtons of force. 100 newtons of force. At the same time, I could look at block 2 instead. If I look at block 2, there's just that tension force. Like the 150 is only directly acting on block 1. Block 2, though, has just that tension force. So if I write out the equation for this one, I have m2 times A is equal to T. That's it. That's my equation. This T is pulling this thing forward. So the mass of T is 20.0 kilograms. The acceleration was 5.0 meters per second squared. That's equal to T. Please notice how T is equal to 100 newtons. So it didn't matter which one we did. So it's actually a great way of checking your work. If you have time, you solve for one, then you solve for the other. They will be equal because Newton's third law states for every action there's an equal and opposite reaction.